Hi, everyone. This is a second lecture regarding process and the thread. In the previous lecture, we explained several important concepts um, related to process. In this second lecture, we're going to learn how to create multiple processes running concurrently. So, what are the operations on processes? Three commonly seen ones: process creation, process termination, and process join. Some we call process join as process wait. The meaning of process creation is obvious. We create a new process. The newly created process is referred to the child of the original process. And the original process is the parent. So a parent process could create as many child processes as possible, as long as the system has the resource to support it. In Unix, we use the system call fork to create new processes. You may have learned fork in the systems programming course, but in this concurrent computing course, we will use fork in a slightly different way. We emphasize the concept of concurrency. Process termination means we terminate the execution of a process. You probably have already used the exit system call so frequently. Therefore, in this lecture, we will not talk about exit. And finally, this is the second thing new to you. When a parent process created a child process, the parent would not just create a child process and let go without handling anything. Just let it go. No, we never create a child process for that purpose. Instead, we create child processes to do something for the parent process. As a result, the child process may compute some results that are needed by the parent. Therefore, before the parent process could continue at a certain point, the parent process must wait until the child who is supposed to deliver the results terminates. Therefore, in this case, the parent must wait for the child process to complete. This is referred to process join or process wait. In Unix, the system call wait will be used. So in what follows, we will explain the system call fork and the system call wait. And we will not talk about exit because you are used to it. To create child processes, you need to include these two header files. Types.h is the types used in a typical Unix system. Unix std, that is Unix standard types. So always include these two header files at the beginning of your program. Otherwise, under some system, some constant or some functions may not be recognized. Always program your programs in a defensive way. Don't get into trouble. Therefore, always include the needed header file, even though your program can still compile and run successfully without these two lines under some systems. Then, listen very carefully. The fork system call sometimes is confusing. As we mentioned earlier, the fork system call is used to create a child process. The creating and the created processes are referred to as the parent and the child. So the data structure or the relationship between child and child process, parent process, and multiple child processes and all of the sub-child processes created later on is a tree with the parent at the root. The system call fork does not need any argument. If the call to fork is successful, now the confusing concept comes in here. Listen very carefully. If the call to fork is successful, Unix will create an identical what? To the process that calls fork. Creates an identical but separate address space for the child process to run. What does that mean? Suppose you are a process. Somewhere in your program or in yourself, you call the fork system call. Instantly, the system would clone you as a new copy of you. So this cloned of you is identical with you, but that clone is separate one. So in Unix language, just like we explained in lecture 1, each process has its own address space. The code section, data section, heap section, and stack section. So what Unix does, if the call to fork is successful, Unix simply make a copy of the address space of the caller. Right after this copy is completed, these two address spaces, one for the parent, one for the child, are completely identical. So just a clone, a copy. So after this clone or copy is created, both processes start running with the instruction following the fork system call. Now, let's explain this further. Suppose I am a process and call the fork. If the call to this fork is successful, and you'll see another CK here, identical one, just like twin. Okay, so they are all identical but separate. Now, what if my nose tip is the place where this call to fork is made? Then the clone would have the same here, nose tip, and then both copy, one the real CK, the other the clone CK, will start execution after nose tip. We will see some real example later on, but please remember two magic words. When a call to fork is successful, Unix will create an identical address space separate to the caller. But identical what? Identical to the callers. After this creation completes, both processes will start running with the instruction following the call to fork. There are some other things you probably need to remember. If the call to fork returns a negative value, it means the creation of a child process was unsuccessful. What would be the reason for an unsuccessful call to fork? The system probably does not have enough resource to do that. For example, if someone created so many forks, and each fork would need an address space, a new one, and if the total number of address space is already large enough, for the next call, you may not be able to create a process. So if for whatever reason, the call to fork fails, then the return value will be negative. Now, recall what I said earlier in a call to fork. If the call to fork is successful, then an identical but separate copy would be created. This identical concept not only copy everything from the parent address space to the child address space, but also the program counter. So the program counter following the fork system call in both address space will be the same. Therefore, if the fork system call returns 0, it means that process is a child. Otherwise, fork returns the process ID of the child process. Now, if again, CK is a process, and CK calls fork here, then a virtual CK would be created next to real one, a clone, not necessarily virtual, a complete copy of CK. That CK, because that CK is a clone of the real one, therefore that CK would also have a program counter pointing to his nose tip. So this is the child. When that child starts execution, that would be the instruction following the fork call. And the child would receive 0. Now, because the child is created, that child receives a PID. So the parent, after the fork system call, returns. The return value from that fork system call would be the PID of the other guy. Okay? So the type of this PID in Unix is PID-T, underbar T. We will have a whole lot of example talking about this. Now, 2 more functions. The first function is get PID. If in your process, you need to know what the PID was assigned to you, you call get PID. This function returns the process PID of the caller. And if you wish to know who is my parent process, then you call get PPID. If we create a child and that child would want to know who my parent is, then that child could just call get PPID. It is possible that the calling process to get PPID has no parent. That could happen and will be discussed later. Then get PPID would return 1. The meaning of 1 is interesting. We will talk about it later. So quickly go through it. If the call to fork is successful, an address space that is identical but separate from the caller's address space will be created, which also include a program counter, which points to the next instruction following fork. When both processes start execution, they start at the instruction following the fork system call. So both processes, the parent and the child, could test the return value to make sure whether I am a child. If the return value is 0, then I am a child. If the return value is positive, it means the return value is the PID of my child. And if the return value of fork, it means the call to fork failed, which means there is no child process created. To get the process ID of a process, just call getPID. To find out who is the parent process of this one, then call getPPID. If the caller to getPPID happens to have no parent, the return value would be 1. The PID type is always PID under bar T. Now, here is a very short but simple example. Suppose this is the main program running as the parent process. This program has 2 integers A and B and a PID variable, PID under bar T. Then this parent calls fork. Remember, if fork is successful, then we will have a child created here. This child will receive a complete copy of the parent's address space. And also, the program counter would point to the instruction following fork. Now, if the call to fork is successful, we have this. The child receives a complete copy of the parent, complete identical, and they are separate. 2 independent, there's no relationship whatsoever between the address space of the parent and the address space of the child. Of course, because this is complete copy, the variables used in the parent address space would also be copied along with its value. For example, if A received a value 10 before the call to fork, and then in this child, A would have 10. So after that, if the parent modifies A, this modification to parents A would not affect the value in child's A because these two are in different address space. So after the creation of the address space, the parent moved to the next instruction to be executed, and the child would do essentially the same thing. So always remember, after a successful fork, you create a new address space, which is a complete copy of the parent. Not only this, the child would also have essentially the same program counter pointing to the next instruction following the fork system call. Now, I hope if you missed something, you will pause this video and go through these 3 or 4 slides to make sure you understand the meaning. Otherwise, you can easily miss a whole lot of discussion in later slides. So don't be afraid of pausing it because time is always on your side, unless you watch this video too late. Okay, now, before we move on, we need to discuss some issues with Printf in multi-process programming. Remember, In the first unit, an overview, I joke myself, CK is stupid. Because when you can use one printf, I use sprintf to print everything to a string, followed by a printf. Did you remember that? If you don't remember that, I hope you will watch that video again. But don't worry, we'll discuss this in the next 3 slides. So remember that processes running from the same terminal window share the same std out. We have seen it when we run background processes from the same terminal window. We also see it when we run multiple processes concurrently using the pipe operator. Remember that? And then this is a problem because these processes running as a background, some background processes and one foreground process, when they run from the same terminal window, they all printed the output to the same std out associated with that terminal window. This can cause problems when using printf due to interleave execution. Now, in all of lectures here, we have seen interleave execution over and over. So people used to say, if you are used to sequential programming, it's a very hard time for you to convert to concurrent, parallel, or logic programming. So you have to pay more attention to this course in order to learn something and pass it. So what does that mean by this interleave execution? When printing multiple items using printf from different processes, execution of this printf may be switched in the middle. That is, this printf is not atomic. They won't execute from the very beginning to the very end, because printf is simply a big function. Context switch or interleave execution could happen at any time within printf. And CPU may be given to a different process, which may also use printf to print something to std out. Then we have trouble. Let me use a very simple example to illustrate it. Let's say we have 2 processes, process 1, process 2. So process A set variable A to 10, B to 20, and print out the values of A and B in such a simple way. Process 2 essentially does the same thing, except that in process 2, we use variable X and variable Y and are assigned 100 and 200 respectively. Now, if we run these 2 processes, process 1 and process 2, say those in background, or one in the foreground, one in the background, both will print the value of X and Y and A and B to the same std out. That is the terminal window. So it is possible that the output from process 1 and the process 2 may be mixed on the same line. Why? Let's take a look at. Now, if we execute process 1, after process 1 finishes the work, process 2 starts. That is, one process finishes before the other process starts. We have perfect example. The value of A is 10, the value of B would be 20, followed by X equals 100, Y equals 200. But what if process 2 runs faster than process 1? That is, process 2 finishes before process 1 starts. Then the output will be X equal to 100, Y equals 200 on the first line, followed by A equals 10, B equals 20 on the second line. That's fine. But let's say, because the printf is a large function, so it's possible that after printing A, before process 1 starts printing B, an interrupt occurs, causing process 1 to be suspended. And then the system allows process 2 to run. In this case, process 2 prints the value of X. Therefore, on this line following the value of A equals 10, we will see X equals 100. This is a beginning thought. So let's say a process, we have this execution pattern. Of course, there are so many execution patterns. You can simply permute this statement to find other cases. Let's say process 1 does print A and then gets switched out due to a interrupt. Then process 2 prints X. After process 2 finishes printing X, then an interrupt causes process 1 to come back to print B, and so on. So in this case, process 1, we assume that because converting this value, the value of A in binary to the ASCII code string to be used in this percentage, the D, this added descriptor, it takes time. So it's very probable that after A, move A equal these two symbols to the std out buffer, that is screen buffer. A gets switched out. Then process 2 start printing here. So process 2 prints out X followed by equal, and then process 2 must start the conversion of binary 100 to 100, a string, and the process 2 could be switched out. And luckily, process 1 gets back, so process 1 could print 10 followed by this space followed by B followed by equal. So we see process 1 could print this part. Now, before process 1 is able to print this end of line, the process 2 comes back. Because process 2 has already printed X equal here, so process 2 prints 100 followed by space followed by Y followed by equal sign, and then process 2 must convert the value of Y2 here. So process 2 would be suspended due to, say, an interrupt. Therefore, process 1 to finish printing 20, followed by 20, we have a new line, move to the second line. For now, process 1 has completed its printf, and process 2 finished the printing of Y here, followed by a new line. So in this case, yes, we printed 2 end line, but these two, the first line and the second line, looks very different from what we expect from this printf and this printf. Why we have this? Because process 1 and process 2 prints the results to the same std out screen buffer. And also because process 1 and process 2 could be executed in an interleaved way. Therefore, if you use printf that way, you may see mixed results on the same line. And we have two processes. What you have more processes, sometimes the output would be nearly unrecognizable. So when you are doing program 1, stop using printf and use sprintf to a string, and then output that string with a system call write, which will be discussed here. This is also a simple example. The programs are in the common directory, and also available from the slide directory at the slide web page. The program name is here. So don't forget to include systems types and Unix standard header file. So let's read this program. PID is the type for process ID. We have my ID and my parent's ID. I have an integer and a character array, which is going to store the whole line of output using sprintf. Now, this is definitely not the typical way to use fork, but we will explain it and see typical ways using fork later. So the first call to fork, a child process is created. Here, because of I don't have enough screen space, I rarely check for errors. So in your program, you are supposed to check every possible error because you need to write your program in a defensive way. So now, if this fork is successful, we have two address space completely identical but separate. So both process, the parent and the child, will start the execution with the instruction following the fork, which is definitely this statement. In this, in the parent and in the child, both call getPID to retrieve its own ID. Both would call getPPID to retrieve the parent ID. Of course, if the child called getPPID, the return value would be the parent PID, the process that creates that child. Then we iterate 200 times. So for each iteration, we print this line to this buffer. So this line reads from my ID, my parent's ID, the value of I, and end of line. So the whole line would be saved or printed to buff. Look at it, it's sprintf. If you use printf, sooner or later, you will see some broken lines or mixed lines. So after everything is printed to this buffer, we use write, the system call write, to print this string out. So here, the first argument, 1, is std out. 0 is std in. Of course, you cannot print things to std in, except you use a pipe. So the second argument is the string you wish to print. The third argument is the length of the string. So in this case, we print the whole thing to a buffer, and then print this buffer of this length to std out. So the parent process and the child process, each of which prints out 200 lines. I hope you remember why we use write, sprintf and write, rather than printf and printf. So occasionally, on the slide, due to space limitation, I simply use printf. But I trust you that you will convert this printf to sprintf and write. So here is a sample output. It's very interesting. So for each line from my ID, that's my own ID, my parent ID, and the value of I. Do you see that? So that means when this guy prints, my ID is 19004. Parent's ID is 19004. So the process 19004 created 19087. 19004 created 19087. Okay, now let's look at another line. Here, my parent ID is 19087. My ID is 19088. So 19087 created 19088. Something wrong? Something wrong? No, nothing wrong. We know 19087 created 19088 because we only have two processes. One is the parent, the other is the child. But where does this 19004 comes in? Remember, when you open a terminal window, the system will load a shell into that terminal window. And that shell would take all the command you issued through that the command line of that window. So this 19004 is the shell. The shell program, which is run as a process, control everything you type through this terminal window. So 19087 is the parent. 19088 is the child. I strongly encourage you to get this program, compile, and run it. So if you want to do something odd, you could replace this printf by sprintf by printf. Remove this one and remove this line, and increase this 200 to say 500. Sooner or later, you will see something odd. In particular, when you run this program, the modify program on a busy computer. Running on your personal computer, probably you see one or two. Sometimes you don't see anything abnormal. But run it for several times, you'll see something odd happen. Then we see some typical use. Here, due to space limits, I use printf rather than sprintf followed by write. So here is a program. I declare variable PID to have this type, which means PID will be used to save the return value of fork, which is here. So when I call fork, and if it is successful, 2 copies of this program, including all of the address space, would be created. And the program counter indicates the next instruction following fork, which is definitely assigning return value to PID, right? So both processes, the parent and the child, would save the value returned from the fork system call to PID. Then if PID is less than 0, whoops, we don't have child process. And if the return value is 0, then I am the child. Otherwise, I am the parent. So this is typical way. Get the return value of fork. If it's less than 0, I don't have child process. And if the return value of PID is 0, I am the child. Otherwise, I am the parent. Recall that if you get this one, it means the execution is in the child process, even though the child process would also have this else part, but it will be skipped. Now, if the return value of PID is greater than 0, then the execution is in the parent part. So if you want to do that, normally we write all of the executable statements in a function. Here I call the child. That is, when I am the child, I call the child function to perform the task assigned to the child. Now, if the return value is greater than that I am the parent, then I put all codes in the parent in a parent function. Then when I am the parent, I call the parent function. So the child and the parent simply does essentially the same thing. The parent prints out parent, the value of I, repeated 10 times, followed by parent done. For the child, it also iterates 10 times. Every time we have some indentation with prefixed spaces, print out the child followed by a value. Now, if you don't print the child or the parent, you don't know which value of I is printed by the parent or printed by the child. So here we learn some concept. This is if, else, and else. If, else, if, and else. We test for am I the child, am I the parent, or fork fails. Of course, if you want to run large program, doing it this way is not very efficient. But for simple program, you could put all statement to be executed by the child into a function. From this function, you call other functions. And you put all the statement to be executed by the parent in the parent function. And this parent function may call other functions. So this way, we immediately see a disadvantage. Because in this single program, I have to put all the codes for the parent and all the codes for child into this single program. This program is going to be large. Now, let's execute this program. Due to space limits, I remove the testing for less than 0. So initially, the variable PID is unknown. When the parent starts running, the parent executes fork. If fork is successful, a separate but identical address space is created. And the next statement, the next instruction to be executed is this assignment. So this is a situation when the child is successfully created. Now, when the child executes next statement, this assignment, the return value of fork would be 0. So 0 would go into this PID. But for the parent, fork returns the PID of the child. Therefore, let's say the PID of the child is 123. So 123 would be saved to PID. At this point, everything is the same except that the value you stored in PIDs in the parent and the value you stored in the child are different. The child received 0. The parent received the PID of the child. Then we move to the next statement. Of course, the execution speed would be different, and the interleave execution could occur. But if you read the program sequentially, the next statement for the parent is here. The next statement of the child is here. They have the potential to be executed in parallel or in an interleaved way. So if the execution goes here after the testing to see whether the value of PID is 0, okay, the situation becomes this. The child sees that, okay, my value PID is 0, so I call the child the function. On the other hand, the parent will see this is false, therefore the parent executes the else part and calls the parent function. I hope this is good enough to illustrate the concept of creating Two, creating a separate but identical address space. The return value to the child is 0. The return value to the parent is non-zero. And then a positive value, because PIDs are always positive. After testing, the parent and the child executes different calls. Now, let's take a look at a very interesting short program. Here, I still use Printf because I don't have much space to show you a complete program. So in the .c program provided you in the common directory or the site download page, it's not Printf. So this program is still simple, very similar to the previous one. This program creates a child process. The return value of this fork is saved to PID. So I did not check for whether return value is negative or not. You have to do it. So we test whether the PID is 0 or not. If it's 0, the child executes this part. If it's larger than 0, the parent executes this part. Now let's take a look. Only 3 statements. And if you use sprintf and write, you have 5 statements. So the child have some print the whole thing out. From child, it's PID, get PID, and my parent is this guy. So simply prints out my child followed by from child followed by the child PID. My parent is the parent PID, and the system call slip followed by a positive integer indicates that the execution is suspended here for at least this number of seconds. So after printing, the child will be suspended for 5 seconds, at least 5 seconds. It won't be too long, because when your child process is resumed, it may not be able to get the CPU immediately. So it's going to be slightly longer than 5 seconds. And then print out a child with its own PID 5 seconds later, followed by the parent's PID. So the child's work is very simple. Prints out my PID, my parent's PID, and stop its execution for 5 seconds. And print out essentially the same value, my child, the child's PID, and the parent PID 5 seconds later. And then the child exit, because there's no code for the child. On the other hand, the parent would go here. The parent waits for 2 seconds. That is, the parent's execution will be stopped for 2 seconds. And print out from parent is PID, my child PID. This PID value is returned by fork. Because if I am the parent, the return value of PID is my child PID. So get PPID, if it's parent, guess what? It's going to be the PID of the shell. And then print out from parent done. So basically, we have 2 processes. The parent stop execution for 2 seconds, print out 2 lines. For the child prints out the first line, stop for 5 seconds, and then prints out the second line. Therefore, while the parent is paused for 2 seconds, the child is able to print out his first line, right? The parent execution is paused for 2 seconds, and the child does not. Therefore, child is able to print out its first line. And then child waits for 5 seconds, much longer than the parent spent this 2 seconds here. Therefore, after 2 seconds, the parent will print out these 2 lines. And probably 2 more, even 3 seconds later, the child prints out the second line. So why is this line in slip 5 here? Because when the child starts printing this line, the parent has already finished his work. Remember, the parent pauses execution for 2 seconds, and the child prints here. And then while the child waits for pauses execution for 5 seconds, the parent wakes up. Because it's just wait for 2 seconds. The parent will print out these 2 lines. Printing 2 lines would not need 2 seconds. Therefore, after the parent finishes work, probably the child is still suspended. After the child is resumed, the child prints out this line. At this moment, the parent has already finished its work. And please pause here. And hopefully you understand the meaning of 2 slips system calls. Okay, when you are back, let's run this program. The first line, as I mentioned, the first line must be printed by the child because the child is not suspended. So print it out from child. It has a PID 19292, and my parent is 19291. Good. Then the child is paused for 5 seconds. Just in 2 seconds, the parent is able to print out his first line. From parent 19291, okay, that's exactly this one. My child is 19292, exactly this one. My parent is 19004. Of course, you know this is the shell. Now, after 5 seconds, after 2 seconds, the parent is done. And then the parent is gone. The child finishes the 5 second pause, then is returned to execution. So from child 19292, the same child PID, 5 seconds later, my parent is 1. Whoops, what's going on? From this line, we know this first line and this second line, we know the shell 19004 is 19004 created the parent 19291, and the parent 19291 created 19292. But when the child starts running 5 seconds later, the child still has the same PID. But why? When we get PPID, the return value is 1. The reason is very simple, because by this time, the parent of this child is gone. So this child process becomes an orphan process. It doesn't have its parent process. Should this happen, Unix would return a value of a process called init. This init process is a Unix system process that is responsible to create all other processes. So the mighty God in creating process is this init process. And because it's going to be the first process created by the Unix system, it receives a PID 1. So now everything is clear. Because by the time the child continues, this child is an orphan process. It doesn't have a parent. So when this child calls get PPID, it would return the mother of all processes, which is the init process, whose PID value is 1. Strongly encourage you to run this program, and hopefully you get essentially the same results. Or you may change the value used in the script so that the by the time the child gets back, the parent is still running. What would be a different result? This program is written to show you that when a child calls get PPID, and the system finds out that child process does not have a parent, its parent would become the mother of all processes in the system. That's init process. Now, let's take a look at another interesting short example. This shows you another way to use fork. Let me explain it later on. So we have PID, we have a buffer. This time I have space, so I use sprintf followed by write. So I receive the value 10, J receive the value 20. So here, if you recall, when you learn C, the equal sign or the assignment is an operator. It would yield the results just like addition, subtraction, multiplication, and division. So when you call this A equal B is an arithmetic expression. The result of this arithmetic operator is the value stored in the left-hand side. So the meaning here is just like this. We save the value of fork to PID and test the value of PID. So PID, a fork, the return value of fork is assigned to PID is equivalent to say, save the value in PID, and this expression's result is the value we save to PID. So this is a very commonly seen way in writing a fork followed by assign the value to a PID. So if the return value is 0, then we put 1000 to I, 2000 to J, we print out this line from child, the value of I, the child of J. You would expect that the value being 1000 and 2000. On the other hand, for the parent, its execution is paused for 3 seconds. And then print out from parent. Notice here we have some indentation in the child so that we know which line is printed by which process. The value of I, the value of J. And then write it out. So my question is, when you run this program, you have 2 output lines. 1 line from the parent, 1 line from the child. And furthermore, the parent's execution would be paused for 3 seconds, which means the parent will start printing probably after the child finishes its execution. The child will print 1000 and 2000. So based on your understanding of the system call fork, what value the parent would print? Please pause for a while and figure out what the value of this parent would print. 10, 20, or 1000, 2000. The answer is pretty easy, but I hope you do it. Okay, what I can tell you is you actually have 2 lines for sure. From the line printed out by the parent is 10 and 20. The line printed out by the child is 1000 and 2000. Why? The reason is very, very simple. Because when the child is running here, the child is run in a separate address space. Therefore, even the parent and the child both have the variable I and the variable J. The parent's I and the parent's J are in the parent's address space. By the same reason, the child's I and the J are in the child's address space. They are separate. Okay, so now let me spend a few moments to explain why the use of write is the Printf and write is better than printf. Remember, when write is a system call, when you call write, then the system would have a trap, which is, of course, an interrupt. I call it trap because this is generated by a software. Your program calls write. Then everything will be copied into the system. Of course, don't forget a mode switch. So everything will be copied to the system. This one, and this one. The interrupt handler would analyze what it is. So when the interrupt handler is analyzing it, and eventually the corresponding service routine would get your string and print it up in one operation. Even though both processes may call this write at the same time, but interrupt only occur once at a time. So the one luckier to call write first would get served first. Okay, so before the service to this write completes, the second write's interrupt will be queued somewhere in the CPU. So this is why the use of sprintf and the write is much better than you use printf. Then let's answer the question. This is the output. Child runs first because the parent waits. So the child prints out 1,000, 2,000, and the parent runs on in a totally different address space. Therefore, it prints out 10 and 20. So this example illustrates that the parent and the child runs in different address space. Even though the child modified the value of I and the value of J, it won't affect the value of I and a J in the parent. Then we learn the wait system call. A process calls the wait system call will be blocked until one of its child processes exits or a signal is received. Remember, we talk about signal at the very beginning of the semester, like sick kill, sick int, sick quit, sick stop, sick count, and so on. Sick quit and sick stop, sick count were discussed on weekly reading list 1, I guess. So if a process creates some child process, and if that process wants to wait until one of the child processes completes, then that process calls wait. Now, it's very risky for a process to create so many child process without calling wait. Because if you don't have this wait, then the parent process runs and completes. All of those created child process will become orphan process. This is not a good programming practice. So always remember, if you create a child process, don't forget to call the wait for the completion. So the wait take a pointer to an integer variable and return the process ID of the completed process. Normally, we don't care that integer variable because that is an integer variable for setting several flags. And in this course, we try to make your life simple. Therefore, we don't use these arguments. By the time you get a job to use this system calls, then you know the meaning of each system call, then you dig deeper to find out what each of these flags means. So wait would return the process ID of the complete process. If by the time you call the wait and no child process is running, wait would return -1. For an example, you never create any child process and you call wait, then you get the return value of -1. As I mentioned here, some flags that indicate the completion status of the child process are passed back through a integer pointer. Now, here are 3 possible ways for us to use the wait system call. Here, the call wait followed by a pointer to an integer variable. If you don't care, you just put null there. So if you have one wait, as long as a process is running and that process completes, and you get the return value being the PID. Of course, while you call wait and that process is still running, then you will be blocked here until that process completes. So basically, if you created 4 processes, you probably need 4 calls to the wait system call. Here I have n processes running, and I don't care which one is complete first. So when I zero the first call to wait, the call may be blocked until a process completes. So we have n-1 processes running, then we loop back for the next one and so on. So if we could finish the for loop, then all n child processes have completed. Another way to use the wait is, remember, the wait system call returns the PID that just completed. So we could use a while loop as long as I call wait, as long as return value is not the one I want, then loops back, wait again. So these are 3 typical ways in using wait system call. Here is an example. I create, remember this, call fork, the value would be saved to PID, and this arithmetic expression would return the result we saved in PID. If the child, we call child, and if the return value is not 0, I call parent and wait for the child to complete. So very simple example. Now, before we go on for other things, we need to discuss briefly 2 concepts, zombie or defunct process. A zombie is a process that terminates execution before its parent executes the wait system call. Now, recall in my last lecture, the transition diagram. When a process finishes its execution, its status would be in the terminated state. When a process in the terminated state, the system would reclaim all the resources. But typically, if that process is a child process, a good programming practice would be the parent must call wait to be notified that a process has ended. So when a process terminates its execution, it will be in the terminated state. But if the parent hasn't executed wait system call, that process will be in the terminate state, becoming a zombie. So a zombie process only has an entry in the system process table because that process technically is still in the system, but it does not execution. It does not execute. So it's just an entry in the system process table in which it has each entry records a process in the system, but that process has terminated. So a zombie process does not occupy much system resource. It's just an entry in the table. So a zombie process will be removed completely when its parent terminates, or when its parent executes the wait system call waiting for this child. Once it's done, that system process table entry will be removed, and the zombie is no more in the system. So quickly go through that. When a process terminated, it will be moved to terminated state before its parent executes the wait system call. Those processes in the system process table would just occupy one entry, not much space. So a zombie process will be removed completely from the system when the parents terminates. Probably the parents never care about the child process, or the parents process forgot to execute a wait. Or if the parent is written in a good way, then when its parent execute a wait system call, this child will be waiting for this child, then this child is removed. Between the termination of the child and the termination of this parent, or the parent execute a wait system call, the child is a zombie or defunct process. A zombie process in the terminated state, as we mentioned several times earlier. Now, you may want to think, even though it's terminated, it's still a process in the system. Can I kill them? No. The kill command cannot be used to kill zombie processes because they had died. To find out whether you have zombie process, use the ps command followed by -af. Well, mind you, different systems may use different arguments. So you have to check the manual page of the PS to find out how you are able to see all the zombie processes. So let me create 3 zombie processes. This is not a complete program, of course. The parent create a child, and then continue to create a second, continue to create a third one. So then we have 3 processes running. I hope you add the code so that these 3 child processes would execute a loop that it never ends. And the parent would also execute a loop. Now, if you do not allow these 3 child process, one from here, one from here, one from here, to loop forever, you just allowed it to spend some time. Say sleep for 1 second and exit. Okay, so because the parent loops here forever, and these 3 child process ends early, therefore, in the system, you have 3 zombie processes, the 3 child processes of this parent, and the parent never dies. Now, here's an example showing to you the output. PS-AF. So we see several processes here, okay? So this is my program. some.c. And then you see 3 defunct zombies. So here it shows you process 1313 created 1314 PPID. See that? 1313 also created 1315 and so on. So these 3 are zombie, but this guy is still running. So I try to kill it, 1313. Okay, you still send out the sick kill signal, and then see that again. Kill the parent. So everything is gone. Do you see that? 1313 is the root of 1314, 15, 16. So when you kill 1313, that's killing the parent, everything is gone. Because when the parent terminates, all of your child processes would be removed from the system. The next concept is Daemon process. It's kind of controversial. Some people pronounce it as Daemon, and some people make it Daemon. I prefer the first one. These processes are background process that is detached from a terminal. Remember, we could run a process from a terminal, but we could run them in the background. So that background process would not have std in there. So they are used to answer requests and or to provide services. So those daemon processes are usually some services process there, waiting to answer some questions and respond with some services. So usually these processes would have last letter to be D. Daemon processes are usually created when the system started by the init process. Remember, this is the mother of all processes whose PID is 1. It could also be created by a process that immediately exits after creation, making the created process adopted by init. Creating a process and the terminates. So that process, the created process, would not have a parent. So immediately it will be moved to init's child. We mentioned this several times. Now, most of the time, Daemon process usually have a PPID 1 and have a name something followed by D. So this way, we use ps-ef to generate a very long list of all processes. Check for the argument. I hope you know this arg. Okay, so that is the third argument, which is the PPID. As long as PPID, we print it out. So this means the output of PS is piped to this program, AUK. So this PS would generate so many lines of output. All of these lines would be piped to the program arg. So you may think that each row is an argument separated by space. So the first column is the owner of a process. The second column is the PID of that process. The third column is the PPID of that process. Okay, so that means this PS command generates so many output. And each line of this output will be piped to the std-in of arg. Arg retrieve the third argument, which the third one here, compare its value whether it's equal to 1. if it is equal to 1 and print it out. So this printed out is from org. So as you can see, the PPID column is all 1. And these are all daemon process created by the root and some other system programs. And if you look at the command to run them, you see the name are ended with D. Most of them, not all. So as you can see, if you are not used to command line argument, learning this program is very handy. In particular, if you use PuTTY to log into a CS server, you have only command line. But of course, you could use X forwarding to get graphics. But in this course, the first 2 programming assignments do not need graphics. So most of the time, you just use command line argument. So learning these programs would be very handy for you. So that ends our discussion of fork wait. This, I did not discuss exit. So fork, wait, and exit will be good enough for you to write a very simple program for programming assignment 1. The next few slides are for program assignment 2. These system calls is referred to as exact system calls. Now, what we have learned in creating processes seems to be not very interesting because I have to put all codes for several processes into one program. When a child process is running, all codes for that child process are there, which is waste of space if you write very large programs. So we are able to do something much better. When you create a process, we could run a different program rather than the one given by the parent's code. That is, the parent create a child. That child inherits all codes from the parent. But we have a system, a serial system calls, exact system calls. They allow you to remove the parent call and replace it by a new program. So this is very, very handy. So very often we create a child process and run a different program there. And this is done by the exact system call. We only discuss one, Execvp. So the core syntax is it returns an integer value and followed by the system call name Execvp. The first is a pointer to a string. This string gives the program name you wish to execute. And the second argument is actually the argv argument vector, the same as you learn in writing your C programs. So this is a file name string. Usually, some of you may run the program just a.out return. But some new versions of Unix variants suggest that don't do that. Always put a // prefix. So if you wish to run a.out, you'd better do it /a.out. So // means the current directory. So if you want to run a program called the smart, So you build a string with contents dot slash SMART. And the pointer to that string would be here. And you construct the argument vector and put the pointer here. So basically, this is a program. And hopefully, the system would be able to find this program. And if the program is not in the current directory, well, you have to provide a complete path to that. So here, argv0 is the program name as specified here. argv1 and 2 and so on are the pointer to strings that contains the corresponding argument. So let me quickly go through it. The Execvp would have the first argument as a string of a program to be executed. And don't forget to add // in the current directory. If you run all programs from the current directory, which is usually the case, and the argument vector you constructed here. So the Execvp would return an integer value. So when you execute Execvp in a process, whether it's the parent or the child, doesn't matter. If you call Execvp in a program, the system will search for this binary executable and find these all arguments. Then the system would load this binary executable into the address space of the current executing program and erase everything there. So basically, when you do this, you actually ask the system loader to load this program into the current address space, erasing everything. And then that program will start execution and receive this argument vector. So this is pretty easy to understand. Let's do a very simple example. Here I have string. The program name is CP. CP is a system program. The in array has this.c, which means I have a file called this.c. And out is that.c. I have an argument vector of 4 elements here. The first pointer, argument 0, points to this string. Argument 1 is this.c. Argument 2 is that.c, followed by 0, like here. Hope you understand this. I'm sure you are good C programmers. You know what this means. And then we do something interesting. This program creates a child process whose and the fork return value will be saved to PID. If the return value is less than 0, I print it out. Fork failed. If the return value is 0, it means this execution is in the child address space. So I call Execvp by providing the program I am going to execute, which is CP, followed by the arguments here. And if Execvp returns a negative value, which is Unix convention, if anything, a system call returns negative, it means it failed. Then we print out Execvp failed and exit. And otherwise, the return value of the PID has to be positive. Then the parent waits for the completion of this child process. So while the parent is waiting, the system would load the CP program into the child address space. and provide the CP program with this.c as the first argument and that.c as a second argument, and let it run. Assuming that this execution of Execvp is successful, what we have done? We simply create a child process and execute cp space this.c that.c. Copy this program called this.c to that.c. After this program finished, if it's greater than or equal to 0, so this program has to start running. That is running the cp command. When the cp command finishes, I have that.c in the current directory. So this is very interesting. But please notice that when you execute this CP program, that.c should not be there. So this interesting short example illustrates a very interesting concept. We create a child process to run a command, cp this.c that.c, to make a copy. But this is not very funny. This is what the shell program does when you issue the command, which is our last program in this lecture, although it's a bit longer, but worth it. So this short program tells you how to write a mini shell. Now, think this way. If the shell interprets your command and executes a command within the shell for you, and if your program crashes, you may finger pointing the shell, saying that the shell has a bug. It's not my problem, right? Most poor programmer would do this. So in Unix, when you issue the command, the shell simply creates a child process to run your command. So that is why in the child process you see its PPID is the shells. So if your command fails, or your program fails there, it's your problem, not the shell's program, because the shell creates a child process to run your program. If your program does anything bad, your process crashes. The shell process is still there. Okay, so the concept of writing a mini shell is we create a child process. This process would determine what kind of command you're going to issue. And when I know this command, then I create the child process to run your command. Then wait for this child process to complete, and then I accept the next command. So let's take a look at this function. I did it on purpose using a pointer rather than array. So the parse function returns nothing. It takes a string in and return a pointer to an argument list. So the outer while just scan the input lines. So as long as it's not a 0, end of string. Look here, it's not end of line. When you type an end of a line followed by a return, that string will be ended by a 0. So as long as the current character is not end of line, then we execute the first inner while. This inner while simply skips all white space. Here I define white space as space, tab, and end of line. Okay, so check this string. As long as the current character is not a space, nor a tab, nor a new line. So we simply replace this white space by a 0. Do you see that? Current character is, if it's space, then I set a 0 there and increase to the next one. So keep doing this until we hit the non-space, non-white space. So the first while job is skip all white spaces until we get a non-white space. All the skipped white space will be replaced by a 0, which means end of string. So when we get the non-white space character, then we know we have a new character. So we save the pointer into the next arguments. Now, we know we have the first character of non-white space. Then we have to extract this argument or extract this token. So what am I going to do? As long as this character is not the end of string and it's not a space, not a tab, not a new line, so we know that is typical character. Of course, you could make this while test more complex. For an example, you could detect that all of the digits or characters. So as long as the current character is not one of them, we advance the line pointer. So we keep doing this until we hit a white space, right? So from this, the first non-white space to the last non-white space, we have a token or a command line argument. Then we go back and scan for the next line. Whether it's the end of string, if not, then skip all of the white space and find the first non-white space. And then skip all of the non-white space. Then we move to the next one and so on. So let's take a look at, and finally, when this while ends, we put a 0 to the next one, indicating that's the end of argument. So let's say each of this space here actually it's not only one space, it could be multiple space or multiple tabs, multiple end of line or something. So we scan here. This one is not a 0, nor a white space. So we reach it here. So the first one, argument 0 is here, points here. Then we skip all of the non-white space. Then we hit here, we have a new white space. We replace all of the white space by 0 until we hit the next T. That's the beginning of the next argument. We skip all of them. And also put a pointer in argument 1 to this T. And then we skip all of this white space and replace them by 0. Now we reach this T. That's the beginning of the next argument. So we put a pointer there and so on. So I hope you study this short program. I did on purpose, not using arrays, instead I use pointers. Then let's take a look at the execute program. The only argument for the execute program is the argument vector we constructed on the previous slide. Then here we create the child process. The returned PID would be here. If it's less than 0, we'll print it out. Forking child process failed and exit. And if the return value of fork is 0, it means I am in the child process executing. So we use argument vector 0 as the file name here, and the remaining here. And if the Execvp returns 0, I have a problem. So exec failed. Why we may have this exec call fail? That's because the system may not be able to find your program. Or when loading your program, you do have a program name there, but that program is not a binary executable and so on and so forth. So basically, if you type the program name on a command line followed by the needed command line argument followed by return, and that program cannot be executed, then apparently Execvp would return 0, less than 0. Let me reiterate. When you build this argument vector, you could open a terminal window, type argument 0, followed by argument 1, argument 2, blah, 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 then return. And if in that terminal window, your argument 0 is not a program or for whatever reason, the shell reported you cannot execute it, the same thing would happen to Execvp. So you can easily test this by opening a terminal window and giving issue the same command name followed by command line argument. So if the execution of Execvp is successful, so this child process address space will be erased and replaced by the program you specified in the argv0, the program name. And that program start execution and receive all the argument here. And this part is never executed because the execution goes into the new program. So because we know which child process is there, the main program simply waits for the indicated process to complete. So this part is rather easy. Now let's take a look at the main program. The main program has a line buffer. And the argument vector, I only give it the line buffer of 1024. That is the maximum string length is 1023. And the argument vectors at maximum is 63. So we have a loop. And print out the first line. And this time, because I can use printf without any problem because it's the only program running. So shell print out a prompt and get the input line. So when you print out shell with an arrow, you have a cursor here. The user type in the command line, and then you resend by the use of get s. Remember, this is a warning. Never ever use get s. Instead, use fget_s. So the whole line will be ready and print out a new line so that on the terminal, you move to the next line. Then the input line will be passed to the parse function. That parse function would construct an argument vector. Then we compare the first argument. I hope you have used string CMP, string compare. It takes 2 strings. So we compare whether the argument 0 is exit. If the first the argument 0 exit, then that means you end your mini shell. So that means if you want to exit this mini shell, you type EXIT, or lowercase. Of course, you could make it more complex. For an example, you could also construct a while statement to compare whether the argv0 is the command you could recognize. But anyway, we just want to make your life easier. We use exit to end this mini shell, then end. Otherwise, if the argument vector 0 is not exit, so you execute the program called execute with argv. In execute, it creates a child process and it parses the input line and execute it by creating a child process. Okay, the concept is very simple. You compile this program and run it, and this program would act as if it's a very small shell, reading a line from you and parse it. And if the argument is not EXIT, then you call execute to create a child process and run the command there. When it ends, the child finishes. It means that the command you provided here has been executed fully. And then the executed program returns to the main program, accept the next command. So this is how a shell is written, although that shell is much more complex than this mini one. So this is good enough for this lecture. Keep this in mind. In program assignment 1, you are only supposed to use fork, wait, and exit. You are not supposed to use Execvp, which should be used in program number 2. In my next lecture, we will discuss shared memory. So far, no matter what you do, those processes are running in separate address space. They have no way to communicate with each other. So how can we make sure this process can communicate with each other? That is shared memory, which will be discussed in our next lecture, lecture 3. So program number 1 should be online when you watch this video. Program number 1 is very, very simple. The only thing you need to know is how to create multiple processes, each of which runs a very simple program. So let me stop here and see you next time. And please visit the course website to start working on program 1. My recommendation advice is always start working early, because concurrent programming would need a different mindset from what you are used to, the sequential programming. So see you next time. Goodbye.